After having looked at some of the most common optimizers for optimizing the parameters of deep neural networks, let's now look at some optimization strategies that can help to further improve the optimization results and that are typically used in practice and that are very important to apply. As already discussed, choosing the right learning rate schedule is important. We've already seen that the learning rate should be decreasing. Otherwise, we will continue oscillating around the optimal value. However, it shouldn't decrease too quickly because we might get stuck in a region that is far from a good one. Right. So here is the example again, where with a fixed learning rate, even when initializing at the true minimum, we will not stay there, but we will oscillate around. Right. So a fixed learning rate is not a good idea. It's not a good idea because it doesn't converge. It's also not a good idea because it's too slow in the beginning and too fast in the end. Another popular learning rate schedule is a learning rate schedule that applies this inverse proportional decay that we've already seen, motivated by this Robbins and Monroe theorem. However, this decay is very fast and often too fast. Also observe that here there is, of course, a hyperparameter left. So this multiplier to this decay still needs to be chosen manually and implemented. One can also apply exponential decay, where I have a hyperparameter alpha to the power of the number of iterations t. Again, multiplied with some fixed learning rate eta. And then finally, and what is probably most common in practice, is step decay. So we let the model converge at a particular learning rate. And then once we see that it doesn't change that much anymore, so here's an example from this paper here, where you can see different steps here where the learning rate has been changed. So when it's converging at a particular learning rate, then we start decreasing the learning rate. We set the learning rate to a new value, a smaller value, and then we let it converge at that learning rate, and then we set it again to a lower value and let it converge. And so we can now decide what these learning rate values are, but we can also decide at which iteration we want to decrease the learning rate. Right, that's called step decay. What's common in practice is that we reduce the error rate by a factor of half or a factor of 2. So we multiply a half to this previous learning rate, and we choose the locations of this step based on experimentation. Another thing that's very important when training is to actively monitor the training process. It's very important to get an intuition about this process and how the model behaves in order to understand which hyperparameters need to be changed, if there's some general problem with the model or the data, or if we should choose a different optimizer. So here are some examples of looking at learning plots. So here we typically plot both the training and the validation loss. So that's the most basic thing you can do. And in this case, we observe overfitting, because neither the training nor the validation loss is able to significantly decrease. Right? Starting from the first iteration, we have this small linear decrease, but we don't have this classical curves where we have a steep decrease in the beginning and then convergence. So probably the model does not have enough capacity. Probably we have an underfitting situation in this case. Here's another situation. In this case, we observe a decrease, but we also see that the model probably hasn't converged yet. in this case, we just need to run training longer, and that can mean we can sometimes, in some cases, have to train for very long times. Some models require days, some models even require weeks. So it really depends on the model, number of parameters, and the architecture on how long this model requires to train. Here's another example where we observe that the training loss continues decreasing, but the validation loss starts to increase again. And this is the classical situation of overfitting that we have seen before. So in this case, we might want to use a regularizer, such as early stopping, or change the capacity of the model. But in general, this is a behavior that's quite common in practice. And here is an example where we don't have overfitting, but the training and the validation loss curves are quite well aligned. So this is also a common situation in practice. In this case, we see that the training loss converges and the training curves looks nice here in blue, but the validation curve in orange is very noisy and oscillates. And that might mean or indicate that the validation set has just been chosen too small. Of course, there's always a price to pay. If we evaluate every nth epoch, we have to run the forward pass for the entire validation set. But it's important to not choose the validation set too small, otherwise you will not observe something meaningful. You will have too much noise. It might also happen in some cases that the validation set is actually easier than the training set. And here we can see an example of this situation. In general, it's highly recommendable to use some of the tools that are available in the community for monitoring the progress. And a great tool that almost everybody is using is TensorBoard. It was originally coming from the TensorFlow community, as the name indicates, but there have been many adaptations of this software, so you can also use it from PyTorch. And it allows you to very easily, during the course of training, monitor the learning and the validation curves, also other factors such as not just the loss functions, but maybe the actual accuracy that you can't optimize, but that you're interested in the end, or other things. You can look at individual mini batches. You can visualize individual samples using various visualizations. You can show a graph of the neural network and distributions and histograms of activations. And this is really useful and it's very important to debug your neural network. It's also important to choose the hyperparameters well. What are hyperparameters? Hyperparameters are all parameters that are not optimized by the gradient descent optimization algorithm itself. So, for instance, the parameters of the neural network are not hyperparameters, but the network architecture itself, which is not optimized by gradient descent, or the number of iterations, or the batch size, or the learning rate schedule, or the weight of the different regularizers, is a hyperparameter. So we have less hyperparameters than we have parameters in our model, which is good, but there's still a significant number of hyperparameters to search the space efficiently. Yet this is a difficult problem, and it's actually still the most common situation to manually search that space based on intuitions. Building intuitions and looking into the local neighborhood of where we currently are, looking into the literature. Often papers have a separate section on how these parameters are chosen or specify these parameters in the supplementary. So starting from a good model and starting from there, or starting from looking at related models and choosing the parameters accordingly, the hyperparameters, is a good strategy. Of course, if you have enough compute resource, you can do something like grid or random search, where you define some ranges that you systematically study. So here's a range over the first parameter and the second parameter, and you systematically try out these values until you obtain a low validation error. But of course, this requires a lot of training runs, which are very expensive. Random search is similar to grid search, except that you don't search on a regular grid, but more randomly. And then you can, of course, do this at multiple scales. So you can start with a coarse grid and then narrow it down. Or when you narrow it down, you can always search in a local neighborhood. And it's probably a good idea to still combine this with human intuitions that you have built up, because the parameter search space is still too large to do this efficiently. Yeah, maybe what I should also mention is that there's a whole research area on automatizing this process, on developing algorithms that can automatically find good architectures. This is called neural architecture search. But many of these algorithms are very require a lot of compute and big GPU farms, and therefore can often be used only by big companies that are willing to spend these resources and that amount of energy into getting some percentage out of the model. Yeah, there's also neural architecture search algorithms that try to do it in a gradient based manner, but that's much more difficult, and often these algorithms are only able to manipulate smaller components of the architecture and are not able to explore the entire search space over hyperparameters. So how to start? How do you actually start when you implement your model and you want to train and test and see if it works? It's a bad strategy to build your entire model and then directly run it on your full data set. It will almost always not work, or if it works, it might actually give you the feeling that it works correctly, but it does not. So it's a good strategy to start small. Start even with a single training example and use a very small network, maybe just 1/5 of the layers in your full model that you want to develop. And first verify that the output is actually correct, that your model predicts. And then by overfitting to this one training example, you already can see if your training procedure works, because the accuracy should be 100%. You're overfitting to one sample. So your model is in almost all cases flexible enough to fit this example exactly. If that doesn't work, and you will be surprised how often that doesn't work, then there's something wrong and you need to find that problem before going any further, because all of the follow-up results will be meaningless otherwise. Also, when you overfit with a small network on a single training sample, you have very fast debug cycles, which is of course important. If you run your model, if you train your model for 3 weeks and then you get your results and there was a mistake, then you lose 3 weeks. But if you can do this in minutes, you get your answers fast. And you need to choose a good learning rate. So you should choose one of the common values that are used in practice. Now, once this works, you can start increasing your data set. Increase it to not the full data set, but 10 training samples, and verify again that the output is correct. Overfitting to 10 samples should still yield an accuracy that's close to 100%, because this is a very small data set. And what you can also do is you can measure the time for a single iteration and identify the bottlenecks in your model. Sometimes there's a bottleneck in data loading because the data is always loaded from disk and not efficiently stored in GPU memory, etc., etc. Or data needs to be uncompressed because you stored it as PNG images and not as raw data files, etc. And once this is working, then, and it's fast enough for your purposes, then you can increase the data set size from 100 to 1000 to 10,000 samples, and you can also start increasing your network size. And at some point you should, by observing the training and validation plots, you should see generalization. But it's important to make only one change at a time to identify potential causes of problems. There's also various strategies to improve gradient flow. gradient flow is very important. If we don't have a proper gradient flow during the backpropagation, there is some parameters that are not properly updated. So maintaining a good gradient flow is very important, and you should visualize gradient flow, and you should make sure that it's always proper. So we have already seen that initialization is very important. So you should use proper initialization such that activation distributions remain constant. For instance, Gaussian across all layers with the same mean and standard deviation. Another technique that enforces this constancy of distributions of activations across layers, but during optimization, not only during training, is called batch norm or batch normalization. What is done in batch norm is to, over a individual batch, so capital B is the batch size here, to calculate the mean and the variance of the activations for each individual channel separately. So C is the channel or neuron in a layer here. So you do this for all the layers in the neural network. And then you can subtract the mean and divide by the variance to get a whitened signal over the mini batch. And then, because this is not flexible enough, because you can't add a bias that way anymore. Any bias that is added before is going to be eliminated by this operation. There's an additional learned bias that is added here again. Yeah, so you normalize each channel by the mean and variance over the batch, which is implementing something like this, but during training. And this of course works at training time, because we can do this average over the batches. But what do you do at test time? Well, at test time, you just take an average, a running average of the mean and the variance that has been estimated during training, and keep that fixed. So then this operation here becomes effectively just a linear operation. The entire operation here. Yeah. And we have this learnable scale and shift parameter that we add to the model. And then we can add such a batch normalization layer after each fully connected layer and before the activation functions. And this will help with the distribution of activations during training. There's all kinds of different flavors of batch normalization. What I showed you on the previous slide is the default version, but you can normalize over the batch. There's also layer norm. You can normalize over the layers. You can normalize over the instances, and there's also group normalization. So these are applicable mostly for images and convolutions. One thing that's particularly problematic for deep networks is that gradients are propagated very slowly, because gradients are backpropagated, and if you need to backpropagate for many, many layers, potentially hundreds or thousands of layers, then once you arrive at the early layers, the gradients are very small. Right? And in this paper here has actually been observed that this leads, so this was in the context of improving performance on the ImageNet challenge, where the networks became deeper and deeper. So in this context, deeper networks often perform worse than the more shallow ones. And this is counterintuitive, because if you have a shallow network and you add identity transformations as layers, you just hand code identity transformations, then of course you get the same performance as the shallow model. So the deep model should be, in theory, at least as good in terms of accuracy as the shallow model. Now, the solution that was proposed in this very popular paper here on residual networks is, instead of classical convolutional or fully connected layers, to learn the residual mappings. So there's a skip connection here. This is one block in this residual network. There's many of these blocks. And there's a skip connection here that adds the input to the output of these two layers, such that these two layers just need to learn the delta from X, which is much easier, because Now it's much easier to realize the identity transformation. Right? The identity transformation just is that these two layers here just basically predict 0, so that the input is directly passed as the output. And this is much easier. And it turns out that this is tremendously helpful for learning deep models using these residual blocks within the model. And it's common practice today as well. Now talking a bit about training schedules. If you have a small data set, it's common practice to improve performance by pre-training. This is what almost everybody does. What does pre-training mean? Well, pre-training means you pre-train your backbone. This is all the layers except the last few layers that might be specific for your task. So pre-train this backbone on another task, such as ImageNet, for which a large data set, ImageNet, with labels, ground truth labels, is available. So pre-train that backbone, and the network already learns a lot of useful information about how images are formed through this process. And then you can fine-tune either just the last layers or the full architecture on your target task and dataset that has less samples annotated. And it has been shown that this leads to significant improvements in performance. And so many people just start by pre-trained networks on some task and fine-tune them for their task of interest. This is a kind of a transfer learning. Another strategy, if you don't want to rely on these label datasets, is to use self-supervision, where you pre-train the backbone on a task for which supervision is generated from the data itself, such as a denoising task or an in-painting task. And we're going to talk about some of these in more detail later throughout this course. And then there is curriculum learning, which for some tasks such as optical flow estimation is also extremely important. It depends on the task if you want to use this or not. And the idea of curriculum learning is that we start with learning on some easy data sets and then successively increase the difficulty in the data. So for instance, in the case of optical flow, you start with some very toyish, simple scenes that don't have a lot of complexity to them and learn an optical flow estimator for them. And then you continue training with increasingly more difficult data sets until you arrive at the real data set that you're interested in. And it turns out that this is extremely helpful for some tasks to get good performance. So it's important for the model to learn something easy first and then continue with harder problems. And that's also related to human learning, actually, where it has also been observed that this progression is actually important.